Now, I would like to introduce our moderator, Lars Sandström. Lars is Edmund Optics Senior Business Line Manager for the Precision Optics Business Unit. He has over 20 years of photonics industry experience. During his career, especially over the past few years, he has been spearheading several Asphere projects and is certainly an expert on the topic. So with that being said, let me turn it over to Lars. Lars?
Thank you. I appreciate the introduction. I'm really excited for today's webinar, in which we will discuss the benefits of using Asphere in optical system design and the factors that need to be taken into account during the design process. Moving on to our presenters, I'd like to introduce Amy Franz and Oleg Leonov. Amy Franz is a lead optical engineer from our Singapore facility. She has spent the last few years developing Asphere lens manufacturing processes and corresponding metrology. Amy received her bachelor's degree in physics and her master's degree in optics from University of Rochester. Oleg Leonov, our Asphere business development manager, is working in our headquarters in Barrington, New Jersey. He brings a wealth of optics and business experience from within the optics industry. Oleg holds a PhD degree in electrical engineering with focus on electro-optics from Penn State University. Now, with no further delay, I'm going to turn it over to Amy and Oleg.
Thanks, Lars.
Thank you, Lars. All right, we have a lot of slides to go through today and less than 30 minutes for that. So let's dive straight in, and what's a better place to start than spend a little bit of time to talk about what Aspheres are and why one would want to use them in their design. So the answer to the question why to use them is spherical aberration. So spherical aberration is a property that comes along with using spherical optics. It's when an incident set of light rays do not focus in a small point, but in fact, instead, they end up being focused in different spatial points, which results in a blur that's proportional to the amount of aperture that gets illuminated. This is an inherent property of spherical shape, and it cannot be compensated by alignment, or it's not a result of manufacturing errors. But when Aspheres are used, light can get focused in a much smaller dot. That could be also referred to as diffraction limited dot point, and therefore avoiding spherical aberration blur that we discussed earlier. So what are the benefits of using Aspheres on the system level? On the system level, spherical aberration leads to having to limit the aperture of a lens that gets used, and what's also known as an increase in F number. This may achieve the desired resolution goal, but the net result of it is that the light throughput of such system is quite limited. So using Asphere minimizes spherical aberration, and that leads to a higher system throughput, and also it results in fewer elements that need to be used in the system. So the size and the weight of the design system becomes more. As you can see at the bottom left corner, the same system was initially designed with 10 spherical elements, and by using 2 Aspheres, 4 of those spherical elements were taken out of the system.
So Oleg, we often get questions regarding what type of Asphere that should be used in a specific application. In the table on the screen, we can see that we have 7 major types of Aspheres. And my question is really, which one should I choose?
Oh, thank you, Lars, for asking this question, because this is a very good question. So there's a few parameters that need to be, or new aspects that need to be taken into account while selecting the type of Asphere to be used in the system design. So one of which is the system going to operate over a wavelength range, or is this going to be a single wavelength application? Another one is optical power. The third one, of course, is the cost budget, which is normally a very strong constraint. And last but not the least is the actual optical performance requirement. And I would say that as a rule of thumb, a good starting point would be to try to use power Aspheres.
The most commonly used equation to describe the shape of an Asphere is the even polynomial Asphere equation. This equation describes the sag C of the lens as a function of the radial distance r from the center of the lens. If you look at just the first term in this equation, you'll notice also the capital R, which is the vertex radius of the Asphere, and K, which is the conic constant. If you only consider this part of the equation, it will describe the sag of a conic, such as a parabola or a hyperbola. If you need to correct higher order aberrations, you can use a string of polynomials following this term. There are several other ways to describe an Asphere, most notably the Forbes Asphere equation. However, mostly due to historical reasons, people use the even Asphere polynomial. Most of the metrology and manufacturing equipment that we have use this equation as the default.
One comment here. As you can see on the top equation, the number of parameters that would need to be optimized is infinite. Infinite number of parameters is not something that we could optimize in reality. Fortunately for us, the limitation comes from such aspects as the machinery that's being used, and in our case, the machines take no more than 10 parameters. So designer's job is now simplified so that only 10 parameters would have to be optimized. Let's take a look at the merit function, or some may refer to it as an error function. It depicts the quality of performance of an element, optical element, a lens, while it's being optimized. There is a notion among some engineers that are starting to dabble with designing an Asphere for the first time, that the more coefficients that end up having non-zero values, the better the design is. Well, the reality of this is that it may not necessarily be the case, but most certainly, as you can see here in the graph, the more coefficients there are that have non-zero values, the more local minima are being introduced. Those local minima are creating a higher chance that during the optimization process, a convergence is happening to a local minimum instead of the ultimate minimum. And that would result in a suboptimal performance of the lens to be designed.
So one method that you can use during the design phase to avoid these rapid oscillations in the merit function is to begin your design using only spherical components. This makes it easier to find the global minimum, and then once you get into this optimal design space, then you can open up one or two of the surfaces to be aspheric.
In our engineering community, we identify three methods for optimization. So method C, that you see at the top of the list, is the most straightforward one. We take the spherical equation and we start optimization left to right, starting from the radius, then conic coefficient, A4, and so on and so forth. Our experience shows that the first three parameters, RK and A4, they end up competing with each other. So we would recommend that either method J or R would be used in reality, and as you can see, method J would leave conic coefficient till the very end of the optimization process, whereas method R would leave A4 till the very end. Another recommendation we could make here is that try to use several methods and see which one would lead to a better design. But at the very end, it's really up to the designer to decide which method to use.
And one thing that you may notice about all three of these design methods is that none of them is mentioning the A2 or the square term in the polynomial. We do occasionally see designs that need and utilize the A2 term, but for the most part, you can get away without using it. So if you avoid using the A2 term, it can make your optimization simpler.
All right, now. So we have an equation, we optimize the parameters in it, so we seem to be ready to give the drawing to a manufacturer. Well, the question is this a manufacturable design? Or even if it is manufacturable, is it going to be too cost prohibitive, too difficult to manufacture that it would not be accepted by the cost would not be accepted by the customer? So things to keep in mind before you submit a design to a company like Edmund would be they're listed here. So first and foremost, the material that the lens would have to be made of. One should take into account the aspects of manufacturing processes, such as grind, polish, and finishing. Also, during manufacturing, we have to use metrology. So what kind of equipment that we would have to use to meet the specifications that are coming from the customer. And also, would such design be codable? Let's start with materials. So hardness is the first parameter that comes into mind. The harder the material is, the more difficult it is for us to process it, therefore the cost goes up. Same goes for abrasive resistance. On the top of it, both grinding and polishing, they are not purely mechanical processes, they're also chemical ones. We deposit slurry to soften the surface, and that's the chemical process that we're counting on to accelerate the manufacturing process. But if the material has a very high acid resistance, it results in a longer time for us to process the material, and therefore the cost goes up. Another factor is that if a not very common type of glass is required to be used for manufacturing, in other words, that this material is not listed, not shown in this graph, that's actually available also on our website for the reference, then there are chances that this material might not be actually available today on the marketplace. So a delay in procuring such material may happen, and that delay is not limited to a few days, but it could be actually months, if not years, before we get a hold of such material. And as you can see, all these parameters would have a direct effect on cost.
The glass selection can also have a pretty big impact on the ability of the manufacturer to achieve surface quality specifications. So first of all, if you look at the new hardness of the glass, if this value is extremely low, that can make the glass more prone to scratches during manufacturing. The acid resistance, along with other chemical sensitivities, will make the glass prone to staining, which can affect your surface quality of the final product. Okay, now we're going to go a little bit more into the manufacturing details. We will talk mostly about CNC manufacturing, which is computer numerical control, and a little bit about diamond turning, since those are the primary methods that we use. But there are other considerations to take into account for molded optics. The manufacturing process for Aspheres is fundamentally different than what you might be familiar with from spherical lenses, and it leads to different constraints. So for spherical lenses, typically the grinding and polishing tool contacts the entire surface of the lens simultaneously. But for Aspheres, because they have a unique shape, the radius of curvature is constantly changing over the surface, and this requires us to use a much smaller tool spot size. A potential issue due to the sub-aperture tools is that as the tool travels over the edge of the lens, uneven pressure distributions can cause large spikes in irregularity, particularly close to the edge. So the ideal case for us would be if the distance between the clear aperture and the outer diameter were at least the size of our polishing spot. That's not always the case, so one thing that can help in that is if you design the lens to have a little bit thicker edge thickness, and that would allow us to increase the diameter of the part during polishing, and then once that's complete, we can etch down the final product. Some of the specifications that you may put on an Asphere will just increase the cost, and then some of them will make it impossible to manufacture. One of the major constraints that comes up for us in CNC grinding and polishing is a limit on the concave radius of curvature. This is simply because the tool has to be able to fit in that small area. So for our machines, the limit is roughly around 25 millimeters for concave surfaces. And for diamond turning, fortunately, this is not as much of an issue because the diamond tool is much smaller. If extremely tight tolerances on irregularity are required, this is something that we're capable to do by adding an additional post-polishing corrective step, such as the MRF. This machine uses a magnet to precisely guide a magnetic polishing compound over the lens to remove the high points in the irregularity. So keep in mind this is always an option to use, but it will also increase the cost because it's an additional step.
Amy, a common question we get is around metrology. So the customer often asks us, what metrology do we have to ensure the proper quality of the part that we deliver?
Yeah, I think this is a really critical point to highlight, as it's easy to forget about metrology as being part of the manufacturing process, but it's absolutely necessary to confirm that we're making the parts. So we have several different metrology options available at Edmund. Just broadly speaking, we'll divide them into profilometers and interferometers. So for a long time, the industry standard has been to use a 2D contact profilometer, which drags a ruby or a diamond stylus over the shape of the Asphere to measure the irregularity. So we also have, in addition to a 2D profilometer, 3D profilometry. A 3D measurement is required if you want to locate any non-rotationally symmetric errors, such as astigmatism. And a profilometer can also be contact or non-contact. Also mentioning here coordinate measuring machines, or CMMs, which use a probe to probe over the surface of the lens to get a full image of what the lens looks like. The next topic is interferometers. So interferometers use an ideal reference wavefront and to compare it to a wave that's reflected off of the lens surface. It's most commonly used to measure planar and spherical surfaces, mostly because the planar wavefront and a spherical wavefront are relatively easy to produce. A problem with Aspheres, though, is that it's difficult to make the ideal reference wave in the shape of the Asphere. So for some Aspheres that have a low aspheric departure, which means that it's pretty similar in shape to a sphere, it's possible to use a basic interferometer. It's also possible for some conics, such as parabolas. One way that we can take a spherical wavefront and convert it into an aspheric wavefront is to use a computer-generated hologram, or CGH. So this additional optical element used with the interferometer will convert the wavefront to match the ideal wavefront. It's a very effective method, but it does tend to be prohibitively expensive if you're only getting a couple lenses, just because you have to purchase a new unit with every single shape that you make. A more flexible interferometric option is to use stitching interferometry, such as the ASI. This machine would take multiple sub-aperture aspheric measurements and then stitch those measurements together for a full aperture measurement. This is an ideal method to use for low and high volume for lenses that do not have inflection points. Okay, here we have a high-level chart of the metrology that's available for Edmund to use. Unfortunately, with metrology, there's no one machine that's the best for all possible Aspheres. So the first things that we would consider would be the geometry and the precision needed. Once you find a suitable piece of metrology, each of these will have a different measurement time and an associated cost.
So Amy, during the registration to this webinar, we received a question around tolerancing of Aspheres. That seems to be a hot topic. Can you elaborate a bit on this topic?
Sure. So when first starting out with Aspheres, it can be a little bit tricky to know where to start. But some of the tolerances are very familiar if you've done tolerancing on spherical lenses, but there are a couple that are unique to Aspheres. So if you look at the polynomial terms in the Asphere equation, it could be overwhelming if you think that you need to put a tolerance on every one of those terms, but fortunately that's something that you should not do. You can start out with just doing either a peak to valley or RMS irregularity tolerance like you would do on a planar or spherical part. Another tolerance that is not strictly required, but is really useful for the manufacturer, is to allow the vertex radius of the Asphere to vary a little bit, or to give a power tolerance. So in most cases, the power or radius change can be compensated for in the system, so it wouldn't affect the total performance. The picture on the right gives an example of how this is useful for the manufacturer. So this shows the irregularity measurement on the same lens. However, in the bottom one, just by allowing the radius to vary by a couple microns, you're able to cut the irregularity measurement in half.
I'd like to add a couple comments here. So one of which is we would like to discourage our potential customers from overspecifying spheric lenses. They are not the cheapest to manufacture, so overspecification leads to a longer than needed and harder than needed manufacturing process that results in higher costs and higher prices. Another aspect is please consider moving some of the tolerancing off of the Asphere component and moving it towards the redistributing on the system level, either into other components in the system or via some type of alignment compensation.
Another tolerance that is usually used for Aspheres, but not necessarily other components, is a slope error. So due to the sub-aperture grinding and polishing, the characteristic errors in Aspheres often look different from what you would see on conventionally manufactured lenses. These are often referred to as mid-spatial frequencies because they fall in the frequency range between roughness on one end and low frequency form error on the other end. If you look at the example on the right, both of these are irregularity measurements that would show the same peak to valley irregularity. But it's possible for a given system that one frequency would cause poor performance and the other one would perform fine due to the frequency of the error or the steep slope in the error. This kind of effect is often controlled using a slope error. So first, the designer would specify a window size, which will target a specific wavelength. Then this window is placed over the irregularity measurement, and a best fit line through the irregularity measurement is calculated. This line will then have a slope angle, and that slope angle can be tolerance.
Alrighty, as we haven't had enough of things to keep in mind during the design, here's another one, the manufacturing process itself. So in this slide we have two versions of the same system that are expected to yield same optical performance. So at the top we have the molded Asphere based system, version of the system. And as you can see that the molded Asphere in this case has somewhat more of a complex shape. We're showing points of inflection here, for example, and that leads to somewhat simpler shapes of other components in such system. However, one thing that needs to be kept in mind here, we have to make sure that this lens remains to be moldable. What is moldable? So there are two things that need to be taken into account, the thickness of such lens and the ratio of diameter to the central thickness or the thickest part of the lens, as they have to be kept under a certain limit. On the other hand, one should try to avoid making an Asphere that is expected to be ground and polished from being having too complex of a shape. Complex shapes for ground and polished Aspheres result in a longer and more complex manufacturing process that inadvertently results in higher prices.
During the design phase, if you can take into account the specific limitations that are imposed by both your manufacturing and metrology methods, it can help you to create a more cost-effective and achievable design from the beginning. One way to do this is to create specific macros that place limits on things such as the edge thickness, minimum local radius of curvature, or points of inflection.
In the previous slide, we talked about molded Aspheres versus ground polished Aspheres. So the question is, how do we design towards one of those processes, or any other process for that matter? Because the standard software package does not have a check mark or some radiant point that says, okay, I'd like to have it moldable, or I'd like to have it ground polishable. So what one has to do in this case is to go and change the default values for the parameters used during the optimization. Now the question is, what values to use in that case? This is the type of knowledge that comes along with experience. But what if you do it for the first time? In this case, well, a couple of things you can try to do. One is to play around. One of our key contributors in our organization refers to this playing a video game. So you can tweak around and see what kind of results you end up having. On the other hand, another approach could be used when you reach out to a manufacturing house, such as Edmund Optics, and we will do our best to help you to come up with a design that reaches your goals. Alrighty, so as you can see, none of that is super simple. But we are doing our best to simplify the process somewhat, and one of the projects we're currently working on is to introduce a new functionality to our website that would allow one to enter the parameters of an Asphere design into the tool in the website. And the website would provide immediate feedback on whether this design is actually manufacturable, and even if it is manufacturable, how complex it's going to be. If it is complex, then most likely the cost is going to be pretty high. Alrighty, so we've reached the end of this presentation. We're certainly hoping that some of this information that we shared with you today would be useful, and please do not hesitate to ask questions, and hopefully will be able to help you out with your process of designing Aspheres.
Thank you, Amy and Oleg. Please note, we still have a team of expert engineers answering your questions you've submitted in the Q&A. They will continue to answer your questions after the webinar has concluded. I also would like to bring up a couple of questions that was handed in during this session that I think is sort of interesting for a bigger audience. And I have two that I've top of my mind here. And the first one is for Amy. Is there a rule of thumb regarding the aspheric slope that makes it easy to make?
Sure. So in our factory, we have a set of standard metrology that we generally use for grinding and polishing. It can generally measure up to about a 50-degree slope. This isn't a hard limit though, because we do have other pieces of metrology that don't have any problem to measure a full hemisphere out to a 90-degree slope. There also might be some challenges to consider for coating these lenses, but those coating limits probably won't be that different than what you would expect from a spherical lens.
Thank you. So the second question that we have that is on a different topic, it has to do with molding, which is in Oleg's court here. What is the aspheric profile accuracy that can be achieved with molding? Is it better or worse than polished Aspheres? So what is the limit?
That is a very short question, therefore I'd be more than happy to address it. We have a number of molded Aspheres in our catalog, and on the best side of performance, irregularity would be reaching somewhere between a wavelength and half of the wavelength. So that would be the answer to this question.
Thank you, Oleg. And keep in mind, if you have any more questions, contact us and we can ask them further. Thanks, Amy and Oleg. That covers it.
And thank you, Lars. That was some great moderation there. And thank you, everyone. We appreciate you being here. Just a reminder, a link to today's recording will be sent to all participants shortly. You can also reach us via email, the Edmund Optics 1-800 number, or through the live chat feature on our website. So thanks again for joining us today, and we look forward to seeing you next time.
Thank you very much for your time.
Thank you.
Thanks.